All right, so this is a video about materials. So I'm going to be talking about different materials such as carbon fiber, steel, titanium, aluminum, glass fiber, G10. Which one's stronger? Things like that. Really quick. I'm going to make a quick little thing. Carbon fiber is not stronger than steel. Titanium is not stronger than steel. Carbon fiber is stronger than steel. Titanium is stronger than steel. Wait, what? Those are contradictory things. The thing is, it all depends on the application, and it depends on how the forces interact. Now, I am going to give you the densities. I have all the information here, and I'm going to talk to you about the differences between, say, carbon fiber steel, high carbon steel, etc., and why you may pick one over the other. But before I do, I'm going to show you these little balsa bridges. So these are balsa bridges that I actually, I designed and I made, and I show these to some of my students. This is for our class. We have little competitions where we load the bridges. Now the deck only has to be a maximum of 15 centimeters, and as long as a car can roll over it, we're good. That's what has the gaps, because it's the winner is determined by the ratio of the braking load versus the mass of the bridge. This one here is based on a 90-60-30. It's less than 90 though, a little more than 60. So, but it's based on this bridge is as strong as can be. I mean, this design is huge. Let me just explain why. Balsa is incredibly light. So forces are applied here. They go through here. So I'm ignoring this for now. They go through here. So this is going to want to push out. But as the legs are being pushed out by the mass here, these are pushing this up, which is using this as a spring. So this is opposite and equal reaction. This is pushing these back in, which pushes these legs in and doesn't let them spread out. So balsa bridge, if you've ever done that, pretty fun stuff. Super light. Here's another design. This is another design that I've beat my students with just for fun. This one's actually super light. I don't remember if this is 36 grams or 46 grams. But this is based on the principle of rollers. And this actually comes off, so it's not attached. And what I mean by principle of rollers is those anchors just kind of hold the deck in place. But because the deck is not fixed to the legs, I can apply weight here. And if you were to actually see, let's move this down here. I mean, that's a lot of force I'm applying, but the legs are still stable. Why? Because these are not fixed joints, so they allow the deck to flex and roll. So this is something that I do for kicks and giggles. I just enjoy. But let's get rid of balsa. Now, if you look at wood, wood is actually a very good material. I mean, humans have been using this for centuries. But wood is incredibly strong going this way across the grain. Very, very strong, right? If I try doing that, very strong. But wood is surprisingly weak along the ligament bonds. So if you go with the grain, this is actually very weak. This board is actually already broken. It's broken right here. This is generally what I solder on or use hot stuff for my RCs. But that's an example. So if I were to load this way, where a mass would be going this way and just apply force, this board would be quite strong. But if I load it this way, it would be actually quite weak. And this is something that applies to materials. Now, let's go to carbon fiber. This is an example of carbon fiber. This is an X-ray X4 actually. And carbon fiber is very, very strong. Many people will tell you it is 5 times stronger than steel. Yes and no. So the thing is that per volume, steel is going to be stronger, as I'm going to show you. But per weight, carbon fiber is far stronger than steel. And that's where it depends. It depends on what you're using it for, how much you're using. So if you look at this is quite thin. And this carbon fiber, the way it's designed, it's actually quite flexible going this way. right? So if I flex it, it's actually quite flexible. I can take impacts. It's very good at taking impacts. Now, something that you have to do is you have to put CA glue all around here, because here's the thing. Carbon fiber will split. It will chip. It will split. And those are some of the issues because of the lower tensile strength compared to other materials. Now, what is tensile strength? Tensile strength is the strength a material has when in tension. So if I try pulling the carbon fiber apart, or let's just say twisting it. Now, bear with me. I'll make sort of a little graph to make an argument as well, because carbon fiber has a life, and that's something that's very important. Steel does not. Now here, we have an aluminum chassis. Right here, this aluminum chassis is very rigid, but it's mainly because of the design, the folds. Now I'm going to talk about densities, everything in a bit, but this is surprisingly strong. Now, can you get chassis that are carbon fiber? Sure you can. G10 is probably a better choice on something like this, though, than carbon fiber. Why? Because it does not chip like carbon fiber does. Now, carbon fiber is a great material, don't get me wrong. It's used for lightweight, high-strength applications. You have, well, spaceships, aircraft. A lot of things where you need to save weight, but you need strength, will use carbon fiber. Aluminum is another choice. That's why you see a lot of planes will use aluminum for the wings, for example. The thing with aluminum is it also has a life. So let me give you an example of carbon fiber. There are some helicopters, for example, that use carbon fiber blades. They generally get replaced every 20 years because of all the forces that they experience, the bending of the helicopter blades. They just replace them. It's better to replace them than to risk them breaking eventually, because what is meant by it has a life, it means it gets weaker over time. Aluminum also has a life. Long time ago, in one of my earlier desperate jobs, the place I was working for, we're actually hosting an event sponsored by Specialized Bicycles. They brought in a bunch of bicycles, and there were bicycles there from all price points. Some of them were $25,000 at that time, and that was a long time ago for a bicycle. The thing with aluminum is, let's just say you break the frame. Are you going to weld it? Sure, go ahead and weld it, see what happens. It's going to work for a while, but after a while, that weld point will stress and it'll break again and again and again. And hopefully once you break that bicycle frame, you just scrap it, or else you're probably going to injure yourself. Unless you're using it for light duty. Maybe somebody else broke the frame and they were using it for, I don't know, some race competition or something, and then you're just going to cruise, so it's probably not going to experience that many forces. That, I guess, could be acceptable. But I would still say just get a new one, if it's in your budget. So aluminum, after a while, will have to be replaced. But on a chassis like this, it's probably never in its lifetime, or your lifetime, going to experience the forces, assuming you drive it properly, that will cause this chassis to fail. Therefore, aluminum is actually a very good choice. This car, I mean, most people do not keep these cars for, let's just say, 20, 30 years. So who cares? All right, you're just going to pick up a new one, so that's going to become a scrap car. Now, one of the things I do like about the X4, not that I'm promoting the X4, is it does have plastic. So this plastic, the arms, are actually carbon fiber embedded in the plastic. That actually gives more strength and more flexibility, sort of the best of both worlds to the arms. That's one of the things I like about them. Now, I'm going to put this aside. This is G10. Now, there's a variety of, there's different types. There's just your standard G10, which is strong, and then there's the G10 FR4, which is the best. Now, one of the things about G10, glass fiber, and carbon fiber, which I have the carbon fiber over there, is the epoxy that is used is really going to make a difference. So that's why it's difficult to just make a blanket statement saying all G10 is this way, all carbon fiber is this way, because that is not true. The epoxy that is used is going to determine a lot of the strength and rigidity, as well as flexibility, right? Rigidity, flexibility has to do with it. But this G10 chassis, this is very strong. It's lightweight. Now, one of the beautiful things about G10s, they've been using this on knife handles for a long time, carbon fiber too, but this does not chip, split, or crack like carbon fiber does, which is why this is a good choice. Now, the regular G10 is actually less expensive to make than carbon fiber. Beautiful thing about carbon fiber, though, something like this, is if you layer multiple sheets, depending on how you orient them, you can change the flex characteristics of the carbon fiber, which is brilliant. If you follow Formula One, look at Formula One. Those are some of the strategies they use on different parts of the car, such as the wings or other components. Now, chassis, plastic. Now, plastic, I don't have the information here because there's so many different types of plastics. Plastic is by far the weakest, but it's very light and it's easy to mold. So if you look at a plastic chassis, just like this, where it gets its strength, it's actually from all of these engineered designs. This here, if we were to remove all of that, this thing would sag, it would be worthless. Versus the aluminum one, you can get away with a flat surface. So that's something to keep in mind. Even this G10, because if you want to maintain that thinness, you need to engineer these other forms of bracing to redistribute the forces, similar to the Balsa Bridges. And that's why I started off with the Balsa Bridges. The only reason why these are so strong is because of the shapes, the engineering that went into it. If I were to just grab a piece of balsa, it would actually be very, very flexible. Now, balsa is incredibly strong compared to its mass. So it's stronger than any other wood per mass. So that means that if you use if you have a piece of wood and it's a kilo of balsa, that's going to be a massive piece of wood, and it's going to be stronger than, let's just say, a kilo of, I'm just going to say pine. But a kilo of pine is actually going to be a very small, because it's very dense and very wet. Well, I didn't say dry pine, but that's something to keep in mind. So application matters a lot. If you look at tanks, there's a reason why most of your propane tanks are steel and not, say, carbon fiber or glass fiber. And the reason why is steel, well, one, it's probably less expensive. But two, you can have a thinner tank. It takes up less volume, right? The actual exterior of the tank. Versus if you've seen the glass fiber tanks or fiberglass tanks, those are much lighter, but they're thicker. They're much thicker walls. The same thing would happen with, for example, carbon fiber. They're a lot thicker. Now, here's something else to note. So, when you're attaching carbon fiber to carbon fiber, you cannot thread through the carbon fiber or even the G10. I mean, you could thread, but it's not going to be very strong because it's not going to be able to take those forces from the screws or the fasteners, which is why you always embed a metal, some type of metal, say steel, maybe aluminum, threading in there, and that's how you thread them on. If you've watched Formula One and you've seen, I forget what races, if you recall or you saw this one as well, please put in the comments. But a car, one of the F1 cars, flipped, went over, and then the halo was just torn off of the car. And that's because carbon fiber was actually weak at receiving directions that way. There's a reason why engine rods, for example, you'll have an alloy, usually aluminum alloy, or steel rods, for example, sometimes titanium, but you will not see carbon fiber rods unless it's a one-use drag race engine. Why? Because it cannot take the twisting motion. Keep in mind that a rod is going to experience this motion, right? Assuming the piston is up here, crankshaft would be down here. So there's a lot of twisting motion. Those rods are not going to last. Now, is carbon fiber stronger than steel? Yes, 5 times stronger if you take weight into consideration, weight and volume. So density. If you take density, it is 5 times stronger than steel, but that can potentially be misleading. So I have densities and I have tensile strength or yield points. I already talked about tensile strength. So yield point is the point where something, say, bends and then doesn't come back to its original shape. So it'll either stay bent or it'll break, at which point it's worthless for that application. So imagine this is plastic, right? So I'm here, see it bends back, springs back. So it takes a certain amount of force, but I have not exceeded its yield point. So there I exceeded the yield point, I broke it. So here we go again, bends back, I exceeded the yield point. So that's what's referred to as the yield point. You can do the same thing with different metal things. If you grab a ruler, bend it lightly, it'll spring back. Bend it too much, and you go past the yield point, it gives out. So carbon fiber. Now, carbon fiber, you're generally going to have a density of 175 to 193. That's 1.75. 1.93, and this is grams per cubic centimeter. So if you take a cubic centimeter, so just a little cube, let's just say this were this is obviously bigger, it would be a centimeter by a centimeter by a centimeter of carbon fiber. Tensile strength, again, it's going to depend on the epoxy that is used, can be anywhere from 228 to 500 megapascals. Now, for the purpose of this, if you're not familiar with megapascals, don't worry about it. You can Google it. It's a unit of measurement. If you're used to PSI, then that's what you use. So it's the amount of pressure that they can handle. So if I apply a pressure onto it, that's what it is. Now, again, it's going to depend on the epoxy and how the carbon is layered, how many layers, but cubic centimeter, that's what we're looking at. G10, now here I have the information for FR4, which is better than regular G10. It's also fire resistant, moisture resistant. I mean, this is moisture resistant like you wouldn't believe. Density is 180, so carbon fiber can potentially be lighter for the same volume. That's what this means, or it could be heavier. Again, depends on the epoxy that is used. Now, tensile strength is 276 megapascals. So your average carbon fiber is going to be stronger unless it's a specialty carbon fiber. So G10 is actually going to be stronger than many carbon fibers. Again, depends on the epoxy that is being used. So if I get closer to the camera so you can see those numbers, this is also less expensive to produce, but keep in mind you can make a higher end carbon fiber that's 500 megapascals. Glass fiber. So my truck bed is made out of glass fiber or fiberglass. That's because it's a flare side, right? 94 flare side. So those were fiberglass mainly. Here we have a density of 261, right? Still pretty light per volume. But notice the other two will beat it easily. This is simply inexpensive. Glass fiber is simply inexpensive. Now the density can vary. I do not have the yield point, but these are better. Here's the thing. If hopefully you're never in a car accident or a hard crash, but if you're in a vehicle and the vehicle, let's just say it's new, I'm just gonna say new, and it's a carbon fiber vehicle versus a fiberglass vehicle versus a steel vehicle, I'd rather be in the fiberglass because of the way it absorbs the impact, and then it starts, as it splits, it absorbs energy. That's why a lot of race cars now are carbon fiber. If you look at F1 versus back in the day, nobody really trusted it until, I think it was the 90s. I forget the driver got in a massive accident and survived. But anyway, that aside, it just absorbs energy very well. So carbon fiber does a great job absorbing energy. Now, aluminum. Aluminum's not that great. It's actually quite weak, but it's still light. It's 2.7 grams per cubic centimeter, so it is going to be heavier than any of these options. Just a little heavier than this one, but they're still close, but a lot heavier than these. All right, these are let's see, this is 50% heavier than this, or this is 30% lighter than this. Depends on how you look at it. But if it's just aluminum, it's 90 megapascals. I mean, aluminum is weak as can be. Generally, when we're talking about aluminum, we're not actually talking about aluminum. We're actually talking about different alloys. And alloys can go up to 690 megapascals. So as you can see, there's alloys that are much stronger than carbon fiber, much stronger than G10, much stronger. Fiberglass is weaker than these. Again, depends on the epoxy. That's the reason why wheels, they're generally alloy wheels. And here's the thing, if you run carbon fiber wheels, they're great because they're so lightweight and strong, but they have a life. Eventually you're going to have to replace them. I mean, GT40, they look amazing, great looking car. You will have to replace the wheels. Some alloys, you're going to have to replace them as well. That same place where we held the Specialized event, that same place I used to work at, we held a Porsche event as well. The cars, the wheels that they had on there, I think those were, they lasted 250 track miles. And if they were road miles, I think it was about 2,000 miles. I can't remember. The wheels would have to be replaced because aluminum will give out eventually. Now, if you think of screws, there's a reason why steel screws are stronger because of how you're twisting them. Aluminum screws, man, you're going to be breaking those things left and right. I mean, 3mm screw, yeah, good luck with that. I wouldn't use them. Unless you're really that desperate to save weight, I don't think it's worth it. Try finding a different way or just suck it up and drive a slightly heavier car. But notice there's a reason why screws or most fasteners are not carbon fiber or they're not G10, and that's because they cannot stand forces in different directions. Carbon fiber is only good in receiving forces one way or the other. It doesn't really stand the twisting. Now, yes, I said with the chassis, that it's very flexible and it twists. But as I'm going to explain, it's going to have a life. That means if I twist this, it's going to come back. But at some point during its life, it's just going to give out because it actually loses its strength over time. All of these do. Steel does as well, except there's a caveat there that I'm going to mention. Brass, just for kicks and giggles, I added here. So brass has a density of 8.73. And brass is very, very soft. Its tensile strength is 360, although its yield is 140. So it won't break, say tear, until 360, but it'll actually bend and not get its shape back at 140. So you can see it's quite weak, very weak. But it makes for very good weights because it's very malleable. So that's something to keep in mind. Now steel is strong, 400 megapascals. Wait, hold on. But I was told carbon fiber is a lot stronger. No, it's not. I mean, some of it is 500 megapascals, but this isn't 5 times stronger. So where did this 5 times stronger come from? Right? That's kind of crazy. If we look at carbon steel can be 841 megapascals of strength, so up to 841. That's double, almost double, or just under double carbon fiber. So wait, what's going on? I thought carbon fiber was 5 times stronger than steel, but here they look to be steel either stronger or just as strong, or this slightly stronger, but not 5 times as much. It's because of the density. That's the reason why. If you look at this is 7.85 grams per cubic centimeter. This is a very dense material. That's the reason why. If you look at the density compared to this, it's 3 times denser, over 3 times denser. It's 4 times denser than carbon fiber steel. That's the reason why. So if you're familiar with density, which you should, hopefully. Right, well, next thing you know, you're a young fellow, maybe you're 8 years old, so that hasn't quite been covered. But density, think about that as the amount of mass or material within a volume, a set volume. Say that centimeter by centimeter by centimeter cube. So the more stuff you pack in there, the denser it is. Titanium. Ooh, titanium, right? Everybody says titanium is stronger than steel. 240 megapascals. What? Titanium is weaker than steel? So you have to be careful, one, with wording, and two, the context. Titanium is 240 megapascals, but it's much lighter. It's almost, well, it's just over half the weight. So it's about 60% of the weight. Now, yes, I'm talking about mass and weight, and I'm using those interchangeably, but this is with relationship to Earth. Gravity doesn't change in theory. Therefore, it's going to be the same because weight is just how gravity acts upon a mass. Just clarifying that. But it's incredibly light, which means that you can use more titanium and have a greater effect, or maybe you don't need all that strength. If you need something that only holds, let's just say, I don't know, it only requires 150 megapascals, 200 megapascals at peak before failure, this is going to be super strong and much lighter, so you're going to pick titanium. That's why bicycles have titanium components. Well, some of them do. Versus least expensive bicycles will go with steel, maybe a high carbon steel. If you look at tool bits, these are not very good. These bits right here, if you're familiar with these are made for applications where it's very easy to remove the screws. They don't require that much force. If you ever try using this on something that requires more force, let's just say it was a flathead screw with some thread lock compound and it's pretty stuck in there, you're going to end up bending and twisting this. So this is closer to steel. This is a higher carbon steel. This is not going to bend and twist just like that. And actually there's a very good fellow that lent me one of these at a racetrack. So I remove a screw off of a Creighton because I was working on I was helping out a guy that was there working on a trade. And all he had was one of these because I wasn't expecting to have to do that, so I didn't take my regular drivers. I ended up destroying his bit. And then after that, I ended up getting one of these, and this thing just removed the screw right out. So if you look at this one's actually damaged in the tip, different type of steel, and surprisingly, I was using this with a correct size screw. This also high carbon steel versus this is, if you use something like this, you're going to destroy your screws. You're going to start damaging them. Why? Because this is going to start to give, which means now there's going to be play in the head, and you're going to destroy the screws after a while. So you want to use something like this. Now knives, I actually prefer a less carbon, so more of a steel. They dull a little faster, but they're much easier to put an edge back on and then just keep slicing, versus high carbon steel holds an edge super well. That's why a lot of your box cutters have a high carbon steel blade, but those are disposable. It's very difficult to put an edge on there. I just take, good luck using a stone, just a wet stone to grind those down. So that's the reason why you need to be careful with your tools, which brings me to why in many videos I always say buy quality tools, such as these MIP, high carbon steel. I have no idea how many vehicles I've built, disassembled, fixed with these tools. And they work wonders. Again, high carbon steel. So I'm going to just flip over and draw some little graphs and talk about why it is said that carbon fiber, for example, is stronger than steel. But just to be clear, tensile strength, steel, especially some carbon steels, are actually much stronger than all of these. That is the reason why, okay, if you still want to get an argument that carbon fibers just, if you want to generalize and say it's stronger than steel, tell me why there aren't any screwdrivers made out of carbon fiber. Just tell me that. All right, that's my point. Why? Because carbon fiber is actually weak depending on how the forces are applied. That's the reason why. Now, I'm not saying it's not strong. It's actually very, very strong. I'm just saying you have to be careful and not generalize. Carbon fiber is stronger than steel in some applications. It's a lot better at absorbing energy. But let me just draw a random graph. So let's just say, just for fun, I'm going to do, and this is something that I would have talked about if you had been one of my students. That was actually just middle school. It was 8th grade. All right, so let's just say, so this would be the y, this would be the x. We don't care about anything over there. And let's just say there's a yield point. We don't care what the yield point is. I'm just going to draw a yield point right here. Whatever that is. And it's going to be adjusted for different materials. Now, I don't have my colored pencils here, or my colored pens to do all of this. But wait, maybe I do. This one's blue, but you can't tell on the camera, so it's going to look black. That one's black. Might look a little different. This may work. Then pencil. All right, so let's just say this is steel. So steel, let's just say the strength of steel starts, I don't know, right here. So this is steel. High strength steel, whatever, it doesn't matter. Steel, initially when it's brand new, it's going to start with the strength right up here. And as you use it and it cycles, it's going to start getting weaker, and then eventually it's going to get to that yield point, and it's just going to be constant. So it'll never get weaker below this. As long as you don't exceed this force, whatever this is, this yield point, 400 megapascals, I think with steel, steel will never get weaker, which means it's not going to break, it's not going to bend, depending on the application. It will never get weaker as long as you don't exceed this force. And that is very important. Now, I should have drawn this a little different. I'll draw it this way. Let me change the orientation. It'll make more sense if I do it this way. I apologize. All right, so we have... use a marker. I generally don't like using this because it'll bleed through. All right, so this will be our y, our x. I'm labeling like that out of just habit. And we'll do that. Let's just say this is the yield point of whatever. All right, and we'll do this again. So let's just say steel has this strength. This is steel right here. Steel. You start working it, so steel will get weaker after it's new, and then eventually it'll get to this yield, and it'll just be constant. So it'll never drop below that. As long as you don't exceed whatever that force is, it will never get weaker. So this will be its strength. Aluminum, on the other hand, will say start somewhere over here, and I'll do aluminum. And it depends if it's an alloy or not an alloy. So let's just say it's just regular aluminum. It'll start over here, but then aluminum will do something like break. Now let's just say you have some aluminum alloy. There are aluminum alloys that are much stronger than steel. Alloy. It'll start way over here, and then they will do something like that. And eventually it'll break. So this is what I mean, and not necessarily what I mean, but what is meant by aluminum has a life. Eventually, it's just going to start getting weaker, weaker, and weaker, and you're just going to have to scrap it. Whereas steel, as long as you don't exceed this, you are golden. That's why those old iron blocks and those old engines, you can keep rehoning them. As long as you don't overheat them or anything, just replace the pistons, replace the sleeves, you're good to go. You get an aluminum block. Yeah, good luck with that one after a while. We'll see how many aluminum blocks exist with high miles after 40 years. We're not there yet. Maybe. Actually, there were some. I mean, keep in mind, metallurgy keeps getting a lot better, so the new stuff's going to last a lot longer than the old stuff. Now, carbon fiber, its strength, let's just say it's up here. 5 times more than steel. And then it breaks. The thing is that the initial strength of carbon fiber is so high, so high, who cares? Because this is your time lapse, or this is your cycles, your amount of cycles. Now, we don't know how many cycles, I just did this as a demonstration, but maybe this is 1 billion cycles. So maybe by the time you get here and they get even, for example, maybe you're already dead, and the next generation after you is dead too, and the generation after that is dead too. So it's the generation after that, 4th generation, that actually sees this finally get weaker than steel and finally yield and break. If it's in a different application, such as an engine, you probably won't see that. But for example, let's just say you have a carbon fiber hood, right? You had your, your 2000 Honda Civic, or 96 Honda Civic, 94, that's a year. Honda Civic, or maybe you had a Tensile and you replaced the hood with carbon fiber. Here's the thing with carbon fiber. If it's exposed to the sun, it's going to wear a lot faster. It's going to speed this up. The same thing with glass fiber. Same thing with C10. Steel doesn't care. As long as it doesn't rust, it doesn't care. Aluminum is going to be based on cycles as well. So carbon fiber, cycles, and UV, and even if they have the UV protection, eventually everybody that's had a carbon fiber hood or seen one, they give out. That's why you should probably still paint it, but then you kind of covered up the beauty of it, which is the knitting or the fibers. But you'll see that the carbon fiber eventually, where the metal fasteners are embedded, eventually that's going to start getting weaker. They're going to start getting weak. You're going to start developing some play in the carbon fiber from just opening, closing the hood, or the hood just vibrating, because those are cycles. So keep that in mind when you choose something. And to be honest, if you have a Tensile, the hood is so light anyway, because that sheet metal is so thin, it's not going to make that much difference. You're better off spending your money on something else. But anyway, or if you have a Tensile and you have the before and after weight, let me know. I remember weighing a Celica hood and there wasn't much difference. Actually, I think they weighed the same or very similar. And then we also weighed the hatch. That was a 2000 to 2004 model Celicas. I think that was the 5-year span for those. But anyway, it wasn't worth it. So keep that in mind. Some applications, yeah, carbon fiber is definitely the way to go. So far, I guess the only thing that I've been telling you is that steel is actually a lot stronger than people think. But now we're going to go into the carbon fiber. So where does this whole carbon fiber is 5 times stronger than steel? All right. I'm actually going to need to go back to the previous page. We're going to grab some numbers from over here. So 175, 193. Let's just use the high number, 193. The high number is actually worse. You know what? Let's use 175. 175 is a better number. So we're going to try to make an argument for carbon fiber. Keep in mind, I do love carbon fiber. It looks amazing. It absorbs energy very well. It, again, G10 does not chip or crack as easily, or split for that matter, as easily. Let's see, grams per centimeter cubed. Now, so steel, if you put forces like this, if you put it in tension, so I'm pulling on it, steel is very strong. Carbon fiber will start tearing and giving out. That's why you don't see it in links, right? Have you ever seen a carbon fiber chain? I mean, I have not. I don't know why you would make a carbon fiber chain. Just get a nylon strap. That's anyway, that aside, I'm going off topic. Let's go, we'll do the lower number 2. we can round that to 250. Why not? Let's just do 250. 250 megapascals. All right, now steel, I'm purposely going to use the weaker number. So steel, oops, actually I forgot, 785. And we'll use the weaker number, which is 400. So 400, I don't know why I put that line there. 400 megapascals. All right, so just look at these numbers really quick. All right, so let's go ahead and look at that. Let's go ahead and get a ratio between the densities here. So if we go with 785, we divide this by the carbon fiber. I don't know why I set it up this way. I should have set it up a different way. All right. Now we are going to take this. So this is a ratio. And once we take that ratio, so let's see, I would do it by head, but I don't want to. 175. All right. So this gives us a ratio of 4. I want to call it 49. So 449. I guess I can call it 450. Just 45. So this is going to be our ratio, right? Units are going to go away. Perfect. So this is the ratio in density. So let's say we used the same mass of carbon fiber as steel. Now keep in mind that you're going to have steel that's this thickness and you're going to have carbon fiber that's massively thick, but it doesn't matter. All right? Let's multiply it by its megapascal, because a megapascal is based on the density. We have the ratio here in density, so we want something that's the same mass. So again, we can, from density, we can equate a relative weight. So now we do 240 megapascals times 4.5, which is a ratio. All right, so 200 So this would be able to withstand 1,125 megapascals. Keep that in mind. So that's where you get this from. And if you think about it, I mean, if we divide this, if we bring the decimal places over, 1, 2, and then just divide the 4, so we'd be dividing 11 by 4. This is about 2.8, roughly. So this means that this sample of carbon fiber is stronger than the sample of steel approximately 2.8 times. I put an X for times. That was a mistake. I should have just wrote times. 2.8 times. Well, let's do the same thing, but this time let's use the other carbon. The other carbon, what was that, 800? I believe it was 800 500, sorry, 500. So if we use now 500 megapascals, so let's just say we use carbon fiber, and I don't know why I had to check, and I'm going to tell you why, because I purposely picked 250 to make it easier for me. So let's just say now carbon fiber has the same density. Let's just, for simplicity's sake, let's assume it's the same density, but now it's 500 megapascals. Okay, so it's double the strength, so it's going to be double the amount of times. So that means that this carbon fiber here is going to be 5.6 times stronger than steel per weight. So based on all of this, there are applications that you definitely want steel, such as my driver. There are applications where carbon fiber is the best way to go, such as this chassis. Why? Because I want something that is light, flexible, and strong. Notice that for asphalt racing, you're probably going to get on something like this, the carbon fiber chassis or the aluminum chassis. Or you get a carbon fiber, but it's going to be a lot thicker, so it doesn't flex as much. It's more rigid. Why? Because aluminum is more rigid than carbon fiber. So it depends on the characteristics that you're looking for. How much flex do you want? How many cycles do you need out of it? Again, drag cars, right? You're only driving for a few seconds flat out. Who cares? Put carbon fiber rods on there. If you guys have watched, it's called American Muscle Car. Two individuals there, I forget their names. They did a little competition where they modded their cars. One of them did, I think, a previous generation, and then the other one, I forgot her name. She did the 550 series, so the current Mustang in production. She had a carbon fiber driveline. The car actually destroyed the whole thing. It just looked like a bunch of hairs hanging out of the car. This was on the drag strip. It's kind of interesting. Normally it should have held, but that car just had way too much power. I'm sure she did a great job. But anyway, look it up. I forget her name. Anyway, but those are things to consider. Why? Because it was a twisting motion. That's the reason why. Kind of failed for that reason. I'm not saying they all failed. This one probably just had a defect, or maybe she ended up exceeding that yield point. But keep in mind, again, that when these parts are brand new, the initial strength of carbon fiber is through the roof. It's through the roof, and that's the reason why it's so good, such as helicopter blades. You have something that's incredibly strong for very lightweight, but after cycles and cycles of use, it loses its strength to the point where it's going to end up breaking, even though you're not exceeding the forces that you were applying to those helicopter blades from the initial point. The amount of force has not changed. So this is the initial force, let's just say. But because of the cycles over time, eventually it's going to yield and it's going to break. Aluminum has a life as well. Steel does not have a life. So which is best depends on application. Drivers, you are not going to find a carbon fiber driver, or at least not that I'm aware of, or a practical or useful one. I mean, these can handle so much strength. You can put a wrench here. Notice this little squared thing. Put a wrench here. Or this, if you've ever wondered what this hex is for, this so you can put a box wrench on it and then turn it. There's a reason why they make this, because this is strong enough. Why is this cheap steel? Because if they made this out of the same type of steel, it would break the shaft on the driver where this goes in as you twist. That's why this is the weak point. You don't want the driver to be the weak point. It's easier to replace a bit. Different types of steels, high carbon versus low carbon. Carbon fiber for something that's just going to be a body panel. Carbon fiber is amazing. Chassis, if you look at race cars, carbon fiber. Why? You're going to end up scrapping it anyway. I mean, that car's not going to last you a lifetime. You're probably going to use it one season and that's it. I mean, imagine using a carbon fiber chassis for 5 seasons. No way. That would be incredibly dangerous. The driver would not survive an impact. I mean, the car probably couldn't survive the stresses from the engine. But when it's new, that first season, it's fabulous. Fiberglass, oh my God, that thing dries up like you wouldn't believe. I mean, there's parts on my truck bed that I have to fix, and they kind of broke. So somebody rear-ended the truck. That's what happened. The bumper broke part of the bed. Minor cracks, not too big, maybe about 15 millimeter cracks on both sides. But just from years of the light hitting it and it being exposed, it's so dry now that it's pretty weak. So I have to go in there at some point. I'm fixing her up. I mean, she runs mechanically. She's great. It's just, paint's faded, 28 years, right? Truck parked outside. Definitely need some TLC. But that being said, this is the whole point of materials. If you look at this, you think, why are these made out of plastic instead of carbon fiber? Carbon fiber is stronger, because carbon fiber would snap. The amount of forces, or the yield point, this is actually incredibly flexible. It's not very strong, and what I mean by it's not very strong is it'll bend with much less force, and it will break with little force, but the point is this is springy, it bends. Think about, just your skin, right? Very flexible. Your bones, not as flexible. What's going to give out? Well, it depends on the situation. But I hope this explanation was useful. The biggest thing before going out there and buying a bunch of stainless steel screws to replace all your steel, I like stainless steel screws and stainless steel bolts, they're great. Titanium. Before you go out and buy a ton of titanium screws and bolts, think of what the application is. Do you really need to save the weight? Because if you don't, then who cares? On an RC car, do you want to get alloy screws? If you want to save the weight, go for it. If not, then no, you're going to be breaking them. What carbon fiber components do you want? Shock tower? Carbon fiber is probably going to work just as good as the next one, and it's going to be very, very light, especially on something such as this, right? Carbon fiber, I believe that's 4 millimeters. Does it have a life? Yes, it does. I'm probably never going to experience it because the initial strength is so high. Probably if this truck still exists 4 generations from now, maybe they'll see that thing break. But that's a great component. Why? Because it's high up. I want to lose weight up there to lower the center of mass. I'll give you an example. Aluminum. Is aluminum stronger than plastic? Yes. Let's go back. I didn't put plastic. It depends on the plastic. Some plastics only have a yield point of 70 megapascals and start bending and doing crazy stuff. But let's just say you have a T-Max and you replace the arms with aluminum. That's one of the stupidest things anybody could do. Why? You're going to hit something, you're going to bend the arm. Whereas the plastic one will probably just flex and bend back. The other thing too is, let me use the X-ray as an example. There's a reason why nobody makes body clips that I know out of carbon fiber or G10 or fiberglass. Let me give you an example. These knuckles in here, I've already broken one. Actually, that's the only thing I've ever broken out of this car or the other car. Those are a fiber-enhanced plastic, let's say. There's quite a bit of fiber in there to give it its rigidity. The problem with plastic is it's too flexible. So if you want something rigid, you need to add some fiber on there. They're very, very strong. Could I replace those with aluminum? Absolutely. Is aluminum stronger than this? By far. So why don't I? Because chances are, if I take an impact that's strong enough to break this piece, and I take that impact with the aluminum piece, it's probably going to warp and bend the aluminum slightly to where I probably won't notice, but the car will not drive like it used to. And I probably won't notice it because it's such a small dimension. Maybe if I took it apart and inspected it carefully, I would notice it. But that's the reason why I keep these. Because if you take an impact that's hard enough to break one of those components, that is strong enough to warp your aluminum piece. So be careful. There's certain aluminum pieces that are worth getting, some are not. A chassis this thin? Probably not. You would only get the aluminum for rigidity, but if you don't need that rigidity, keep this. This is actually, surprisingly, it takes a lot of impacts. I would go with the carbon fiber. Same thing with the top deck. Something this thin, aluminum, once you take an impact, especially head on, it'll probably bend it. It'll give out. That's the reason why, if you remember the old shaft cars, there's still some shaft cars out there like the 410, but if you remember the TC4, I used to have a TC4. Those things were cool. Those shafts would bend, and then all of a sudden you'd be going down the road, and then at a certain speed, the car would just start sort of bouncing up and down because of that bent shaft, right? That shaft would be like this, so it was like a jumping rope. So keep that in mind. But those are your materials 101. Chassis for cars, RC cars, carbon fiber G10, great choices. Shock towers, great choices as well. If you have massive monster trucks, I would probably go with shock towers that were made out of steel. Why? Because I probably don't care much about the weight. It's a massive monster truck. But competition, yeah, definitely go for these. Fiberglass, not really. I'll just keep that on my truck bed because it works there, but I wouldn't use it in RC cars. Regular aluminum, just get rid of that. You don't need that. Definitely have to go with an alloy, so an aluminum alloy, which I don't think anybody makes a pure aluminum part. They're generally alloys. They're much stronger, surprisingly lighter as well. Once you add magnesium or other things to it, right? Magnesium is one, right? It's very weak on its own, so whenever you see magnesium wheels, they're actually alloys. If they weren't alloys, they'd catch on fire. Magnesium, oh man, that's fun stuff. That aside, but aluminum is good for certain parts. If you need a little more strength, just be strategic. If it's a part that's a high braking part, you probably don't want the aluminum, and the reason why is whatever force would break that fiber reinforced part is probably strong enough to warp your aluminum. Brass, this is just for weights. That's all you're using it. This should be handling no stress, except for just being held on by steel screws. Steel depends on your application as well. High carbon steel, definitely for your tools. RCs, your screws, you want something like this. Titanium, I don't really care for titanium. It's just if you need to lose weight, but tensile strength is lower than steel. So I would just go with steel. Because keep in mind that the screw is going to be the same size, so it's the same volume. A 3mm by 10 screw is going to be the same volume, regardless of whether it's titanium or carbon steel. Carbon steel, then that screw is going to be 3 times stronger. So why would you get this if you do not need to lose weight? Again, I've never seen carbon fiber screws. There's a reason why they would suck. Right. Aluminum screws, you're going to break these left and right. I mean, you tighten them, if you slightly over tighten them, that head's popping out on a 3mm screw. Aluminum screws, you need something greater. And one of the things too is, I keep talking about yield point. If you're familiar with engines, if you've ever removed engines, there's a reason why you generally replace the head bolts. And the reason why is when you tighten them, you actually exceed the yield point, so that head bolt actually stretches permanently. Sometimes you hear stretch bolts. They're bolts made of steel purposely to stretch, sometimes other materials. So that's why you scrap those bolts, get new bolts, and put them in there. So that's something to keep in mind. So you're going to hit the yield point of the aluminum, you're going to stretch that screw, and then it'll never hold the same after you do. And then if you break it, well, you're out of luck. And any of these materials, well, let's focus on fasteners now. Steel, that is why you always want to, even on real cars, you always never want to over tighten anything. The reason why is steel, it'll stretch. Whenever you're tightening that helix in there, the threads, those are stretching the little screw. And by stretching it, that's what's creating that pressure, right? You stretch the screw, so you're putting it in tension. So the screw is trying to compress again and come back. And it's that force that's fastening the components together, which is where these fail. This one's not very good. Forget about that. Carbon steel is the best. Forget about titanium. Right? If you had a screwdriver like this made of titanium, this would just kind of snap. Steel will start bending. That's something to keep in mind. But anyway, I've been ranting long enough. I hope this was useful, or at least entertaining. Thank you very much for watching, and I'll catch you in the next one.
What? Oh, my hair! My tongue! My rod!